it's already really good technology, but as it even gets more refined, it's going to be a game changer for acquiring as built.
Welcome to the LabVIEW experiment. I am your host, Sam Taggart from SAS Workshops. In my 15 years of working with and training developers, I've had the opportunity to conduct a lot of experiments. Over here, we believe in embracing failure as the essential learning experience that it is. And what better way to learn than from other people's mistakes? In this podcast, I talk to industry experts, colleagues, and friends about their failures and how they have turned them into future successes. I am here today with Derek Kultgen from Argonne National Labs. I've heard of Argonne National Labs, but I'm not entirely sure what exactly they do. So maybe, Derek, you could start out with what exactly Argonne does as a whole and your small part in it. Or, yeah.
Yeah, absolutely. Thanks for having me, Sam. So Argonne National Laboratory is the first national laboratory established by what is now the Department of Energy. We're one of 17. It was born out of the Manhattan Project, but has since then really focused on initially the peaceful uses of nuclear energy. So much of the world's nuclear power plants can actually trace their roots back to research conducted here at Argonne National Laboratory. However, today, Argonne has one of the most diverse research portfolios amongst the national laboratories. We have experimentalists and scientists working on advanced materials to solar and renewable energy, electric vehicles, along with nuclear energy, as well as we have one of the world's brightest X-rays, which is the Advanced Photon Source, a large synchrotron. Its diameter is about the distance of the Willis Tower, so it's a quite large facility. And Argonne also houses Aurora, which is a supercomputer which recently broke the exascale computing boundary. My work specifically is in the Nuclear Science and Engineering Division for the Reactor Safety Testing and Analysis Group.
Okay. So you mentioned that a lot of your focus now is on newer styles of reactors. Do you want to talk a little bit about just like how nuclear power works in general? Because I feel like that's something if you're outside of the nuclear power industry, you might not know a lot about.
Yeah, nuclear energy is just this really, really great phenomenon that we're able to take advantage of. The fact that we can actually harness the energy of unstable atoms that will eventually fission and release energy. And we can actually turn that into something useful like electricity. The current nuclear power plant fleet in the US and most of the world uses what's called a light water reactor technology. So you take light water, you pressurize it so that it doesn't boil. That allows you to go to higher temperatures, thus higher efficiencies in your power plant. It's obviously been a very proven technology. It's quite safe. A lot of the advanced reactor designs have more inherent safety built into them. So just the physics involved make them safe. It's just this natural thing that you can take advantage of. And also different types of reactor spectrums. So the current light water fleet uses what's called a thermal reactor. And the real gist of that is that it doesn't close our nuclear fuel cycle. So a lot of people will bring up nuclear waste, right? They'll say, oh, that's a con to deploy nuclear energy, but it's not really a con because our new reactors will actually be able to take much of that, what people consider nuclear waste, and use it as fuel and recycle it. And so there are a few organizations that are working on that as a commercial aspect. Actually, Argonne National Laboratory pioneered this nuclear fuel recycling back in the day through what's called like the integral fast reactor. So the new reactors, these fast reactors, will be able to recycle the fuel from our current reactors, thus really reducing what people would consider waste. People in the nuclear industry actually don't like the term nuclear waste that's storing at the nuclear power plants right now. We call it spent fuel because we know that there's so much more that can be utilized from it. It's not garbage. So not only will the advanced reactors or the advanced fast reactors be able to leverage a lot of that as fuel, they're also, as I mentioned before, inherently safe through physics. So we work on developing equipment and instrumentation for sodium fast reactors, where instead of using water, we use molten sodium. And just for, people like to consider sodium and salt and table salt synonymous, but it's elemental sodium, whereas, table salt sodium chloride. So elemental sodium boils at a much higher temperature than water. So we actually operate up to 538 degrees Celsius in our loop, which the boiling point of water is 100. So without boiling, we can go all the way up to 538. Some of our other test vessels that we have here actually go up to 650 degrees Celsius. Again, we're just at very low pressures. We're at actually just above atmospheric pressure. So we don't need all these redundant pumps um, and all this backup power to ensure that the system remains safe. It can handle the higher temperatures. We can also take advantage of just kind of passive cooling techniques as well. The fact that the sodium by the core at the bottom is much higher than the sodium at the top. And so you can actually generate natural circulation since the hotter sodium at the bottom will now rise to the top. If you can reject some of that heat, it'll then fall back down and you kind of create a natural loop of just heating and cooling. So there's a lot of benefits to our next generation of reactors that we're working on. As I mentioned, the inherent safety, better economics, being able to recycle the fuel, higher temperatures, thus higher efficiencies. So it's a really promising technology. And, the fact that a lot of these data centers are going to be starved for power and require something that does not emit emissions directly, which nuclear energy does not, makes it a very attractive option. And the fact that it is extremely reliable. Nuclear energy has a capacity factor of 90% or higher, whereas you look at something like solar or wind, you're below 40%, and so you don't need energy storage really for that matter either. You have this base load power that's just very reliable and keeps our hospitals, data centers, and other critical infrastructure energized.
Yeah, I think you did a pretty good job of explaining a lot of that. I mean, the way I think of it, I was gonna say, like, if you think of a traditional power plant, but you have, if it's coal fired or something, you might have a boiler where you have water that you're then boiling, and then that steam turns the turbine. And basically, for nuclear power, at least the traditional light water reactors were basically just replacing that coal fire with the nuclear reaction. And then and that's like the boiling water reactors, and then the pressurized water reactors contain that water and get it to a higher temperature and then run through some kind of heat exchanger that basically then does the same thing, right?
Yeah, basically, there's a few, alternatives to it, but yeah, at the end of the day, we're just trying to replace what your heat source is. So whether your heat source comes from natural gas, coal, we're replacing the heat source from these kind of hydrocarbons to a nuclear fission.
Yeah,
Uh,
so once you
End of
produce the
it.
steam, then everything else is more or less the same.
Yep, pretty much. Yeah, and then I would say the only alternative to that is there are some high temperature gas reactor technologies which actually could use more of like a jet engine cycle.
Ah, okay.
So that's a pretty interesting concept too that's out there, as well as some supercritical CO2. But near term, I would 100% agree with you. It's going to be something that's generating steam to spin a turbine.
So when I worked at Westinghouse, they were talking a lot about pebble bed reactors. Or the sodium, is that like a pebble bed design, or is that a different type of design? Or
Generally, the pebble bed is going to be for a gas cooled reactor, so
okay,
they use helium. So that is another a technology that Argonne also works on here is the gas cooled reactors as well. A colleague of mine actually does research in the same building as us and has a fairly large scale facility that uses LabVIEW as well for gas reactor technologies.
okay. Other questions that I have. The other thing that I remembered hearing a lot, and this was like probably more than a decade ago, was small modular reactors were all the rage.
Mhm.
And so are the technologies that you're working on, are they more geared towards the small modular reactors? Or are they more geared towards larger power plants to like supply an entire city? Or how does that fall out?
Yeah, I would say Argonne as a whole looks at the entire spectrum. Like I said, from microreactors, something that's like a megawatt electricity to 20 megawatt electricity. Small modular reactors are like greater than 20 megawatt electricity and like upwards of like 300 megawatt electric. And then you have your like utility or large scale, which are typically at a gigawatt. Um, so most of the reactors, the sodium cooled ones being proposed are more in the small modular range of reactors. So, I think Bill Gates's TerraPower has like a peak output of 400 megawatt electric. Don't quote me on that value. And I think maybe up towards a 500 megawatt electric peak using energy storage. But their continuous base load is like 300, 350 megawatts.
Hmm.
And that Oklo company I mentioned, I think is around like the 100 megawatt electric range. So as of now, we're mostly focused on the coolant and allowing vendors to scale up and down as they see fit. Um, so that I guess I would say all of the above. We're very heavily focused on again demonstrating technologies, ability to survive the harsh environment of a fluid so reactive as sodium. Also, you're going to have the radioactivity aspect if it's in the primary coolant circuit. So it's really up to the people who are going to commercialize these technologies of how big they want it to be. But yeah, very long-winded answer that uh, we're not so focused on the scale, whether it's a micro, small modular, or utilities or grid scale. Um, we're kind of just focused on making sure that the equipment's going to survive these harsh environments.
I have one more just general question. So I remember at Westinghouse when they're talking about small modular reactors, one of the selling points was that eventually they could get these to the point where they would install them and they'd be like very low maintenance and fairly safe, and you would just kind of like basically you run it with like either a skeleton crew or like no crew at all really, and it just kind of like sits there until you need to refuel it. Is that still like a thing?
Absolutely. I mean, that's the dream. If we look at the personnel requirements, I think the last I heard, like a nuclear power plant's well over 500 people. For an equivalent size natural gas fired power plant, it's like 20. For the most part, a lot of these natural gas power plants are monitored and controlled remotely from a diagnostic center. And, you have those 20 personnel on site to address immediate issues, kind of have the human interface there. But ultimately, that's where the industry's looking to go. Whether that passes the regulatory issues, all of the nuclear regulatory commission's standards is also a challenge. But those are technologies we're working on and demonstrating at our facility is to showcase if you're acquiring large sets of high fidelity data. Again, we're using LabVIEW to showcase that here. But if you're gathering the data, you have a history of operations, you couple that with the physics of the plant, you can now kind of predict where it's going to go. Um, you should be able to have it kind of, in an autonomous stance where an operator is really there to view an indicator remotely and a few people on site to take immediate action. But yes, that's absolutely still something being pursued. And I think my personal standpoint is a requirement for microreactors and is going to be, um, very economically beneficial for the small modular.
Yeah, I can definitely see that because you're not generating that much power, so there's not that much income coming in to pay a bunch of people to monitor it from an economic standpoint.
Yeah, and there's the security issues too. If you have the confidence that you are inherently safe in your design, it can autonomously take corrective actions. I think also is another benefit to showcasing you don't need that much personnel on site.
Yeah, to go back to your earlier point, you mentioned that these new style of reactors are safer because they don't have all the pumps and motors and stuff. And if people remember back to like Fukushima, one of the big issues there was it overheated because all the pumps, something about the breakers were underground and got wet and killed the backup pumps. But I remember that specifically because when I worked at Westinghouse, they were working on this new generation of PWRs, which are not exactly what you're talking about, but it's like the next evolution of the traditional light water ones. And one of their claims was that like if there was an accident, you could basically walk away because you mentioned like the circulation thing. So they had this idea that like if the pump shut off, the water would evaporate and condense on the dome and run back down and recollect and recirculate. So that just kind of ties all that together.
Yeah, absolutely. It's always nice when physics works with you instead of always against you. So,
Yeah, well, I remember studying the Chernobyl thing. That was one of the first things that we studied when I got hired there, and it was basically like the physics of the Chernobyl reactor were actually wrong, and that like whatever they did, it actually like accelerated the reaction instead of bringing it back down. And so that's bad design combined with a bunch
right.
of other stuff.
And I think that's also, a testament to just how rigorous the U.S. is with their safety, the fact that we haven't had anything severe like that. I always look back when people talk about the inherent safety is it's um, it's not that the current fleet is unsafe. It's one of the safest methods to power electricity. It's just there is a lot of overhead required with pressurizing water to achieve that high rigor of safety that we have in the U.S. And if you can, leverage the physics so that you don't have to have these high pressures and have that walk away safety capability, you now have a more economic design as well.
Yeah. So let's talk about your test facility and try to come back to talking a little bit about LabVIEW. So you guys have this giant test facility. What you say you run a bunch of experiments. Can you give me an example of a sample experiment?
Yeah, absolutely. We so with your background in Westinghouse, you have to, no matter what with a nuclear reactor, you have to refuel it. Luckily, the current fleet only refuels like every 18 months to 24 months. New reactors might not be refueling that frequently. They may be refueling every, 5 to 10 years. Some people have even proposed a refueling interval of 20 years. But at the end of the day, you have to pull that spent fuel out and let it decay away in a pool. We actually have designed in-house and fabricated fuel handling machines and basically test articles that operate gears that would be used in these fuel handling machines to evaluate the longevity of them in a sodium environment. So operating at prototypic reactor conditions, high temperature, the liquid sodium, which is very reactive. You can't use any lubrication. Um, you don't have that protective oxide layer that's generally associated with a lot of mechanical on mechanical interaction because the sodium just strips away that oxide layer.
Hmm.
So we do a lot of fuel handling equipment development. We do a lot of instrumentation as well. As dumb as it sounds, it's actually really difficult to measure the level of sodium in a tank. There are a couple methods that you can do to measure how high the sodium is in a vessel. None of them are extremely attractive, other than probably what's called an inductive level sensor. And so that's a technology that we work on, um, is to develop instrumentation like that. And we've also done experiments, what's called the thermal hydraulic experimental test apparatus, or THETA for short. A colleague of mine uses a metal test vessel and basically replicated or miniaturized a sodium fast reactor, replaced the reactor part of it with an electric heater so that you could simulate the heat from the core, and basically replicated a plant so that you could actually see, that natural circulation take place. He would do experiments adjusting, where that cooling was taking place inside of the core to see how that impacted natural circulation, as well as other kind of like thermal hydraulic phenomena that could adversely impact a core. So again, we do everything from real hardware demonstration of fuel handling to more instrumentation, monitoring the plant, as well as more of I would say more of a basic sciences of trying to characterize thermal hydraulic phenomena. And we work with a lot of people who are experts in CFD code and uh, uh, fluids and hydraulics with that. So
Yeah,
really
it's
try to cover the whole spectrum and try to stay as flexible as possible.
Yeah, I was going to ask about CFD because at Westinghouse we used to have lots of people doing these big giant CFD simulations. And so my guess would be then that people do those simulations and then you go and verify it in your test rig. Is that?
Yeah, so there can be a couple of avenues. A lot of times there's just a lot of unknowns, and so this data is actually used to as inputs to the CFD.
Ah, okay.
So it's kind of it's always this kind of circular pattern of, there's some unknowns or some boundary conditions we're assuming. You obtain those, you make those unknowns now knowns or your boundary conditions, feed that into CFD, see how well it works, and you can also use it to calibrate against it. So it's always this kind of circular motion between experiments and then also the more analytical researchers here of just this kind of back and forth feedback. So yeah, it's been a really good partnership. The fact that it's been beneficial to both teams involved.
So I have a question then too. You were mentioning the fuel handling equipment and some of the sodium being maybe not corrosive, but reactive was the word you used. I know in PWRs they had issues with like borax and they had lots of boron in there and it was causing problems chemically. Is that same phenomenon happen then in, I imagine, in sodium reactors as well? Or
No,
similar issues, you know?
no, not to my knowledge. I wouldn't consider myself a core physicist at all, or a neutronics expert, but generally they use that as a poison to kind of
Hmm.
slow the reaction in an emergency. Whereas sodium, you want to keep a pure sodium. You don't want to introduce any kind of contaminant. And then there's also some fuel designs also have more inherent safety where, like I mentioned, the borax would be more of like, hey, we really need to shunt our neutron population. Um, the fast reactor operates a little bit differently, but going back to how this one kind of operates is that sodium fast reactors, for like the metallic fuels, if they get too hot, you kind of have your fuel rods. They'll actually bow out a little bit because they
Hmm.
get so hot. That very, very small bowing is enough for neutrons to escape and cease the reaction.
Okay.
So you not only have the safety from the coolant itself, but just the different architecture from going thermal to fast neutron. You have to have a more honed in kind of accuracy that if you bow that fuel out a little bit from overheating, it just kind of shuts itself off.
That's
And so they,
interesting.
yeah, they demonstrated that back at Argonne West, now Idaho National Laboratory through what's called Experimental Breeder Reactor 2. There's a few, 20-minute YouTube documentaries on that. And it's a really cool reactor that did a lot of firsts. And that was one of the ones they did is they literally tripped off the coolant pumps. They shut them off, let the reactor try to overheat itself and melt it down. And it just, like I said, the physics work out so that it can't and it shuts itself down.
I know when I worked at Westinghouse, definitely with the PWRs, they were very much worried about hot spots,
Mhm.
and they definitely had they had like a flux mapping system they called it, where they drove these detectors up into the core and took readings at different levels to try to make sure it was fairly evenly distributed. I think there they were worried that if it got too hot, I think it like deformed the cladding on the fuel rods, and then somehow the fuel pellets could get out, and then it leaked into the primary water, and that kind of caused some radiation exposure type stuff.
Yeah,
That was like
overheating
the issue, yeah.
Yeah, overheating if you don't have a nice uniform, well, in all reactors you want to have some uniform, temperature
Yeah.
profile as much as possible because any kind of delta T is gonna be undesirable. But yeah, with the PWRs, it's definitely a more serious incident, melting away or having the steam kind of react with that cladding due
Yeah,
to
that was the issue. Yeah. You get that steam void, I
zirconium.
think was the, yeah, yeah, exactly.
Yeah.
Yeah, I forget all the physics, but that sounds very familiar. So another question I have is, you mentioned INC. So do you have to have special types of sensors to detect things inside, what's going on inside the reactor, and how does that work? And are there any like special requirements for like reading out some of those signals?
Yeah, there's so with sodium specifically, there's been some custom developments. Like I mentioned, the inductive level sensor is kind of an interesting technology because it kind of works like a transformer almost, whereas you have basically two bifilar coils inside of a tube that's now sticking in a tank. One of the coils is being energized, and then the second coil acts as like a pickup from it.
Mm-hmm.
As the sodium level rises, it interferes because it's a liquid metal. As the sodium level rises, it interacts with that kind of electromagnetic flux.
Mm-hmm.
And so now you have a decrease in voltage output on your pickup coil or your secondary coil. And so that's a completely custom, instrument that's been developed here in the past, and we're trying to revitalize that technology. There's other instrumentation that has to be, I would say, retrofitted. So like we use standard off-the-shelf pressure transducers. The only difference is because we go to those high temperatures, we have a diaphragm seal and then we have a diaphragm line. And I would say in traditional high temperature applications, you fill that diaphragm line with like a silicone. We go to such high temperatures, we fill ours with a sodium potassium alloy. This sodium potassium alloy, or NaC, is liquid at room temperature, so it works well as a diaphragm line fill. Also, if the diaphragm seal breaks, we just basically insert a little bit of potassium into our sodium, which is not a big deal. So we use standard kind of commercial off-the-shelf instrumentation whenever we can. We just have to do kind of little modifications to make it work. I would say from another kind of cool INC standpoint is for measuring flow rate, we use electromagnetic flow meters. So again, because sodium is a molten metal, we get to leverage the Lorentz forces. So if we have just the right hand rule, if we have our sodium flowing this way, and we have some electrodes on the side and a magnetic field orthogonal to our flow, will actually generate a voltage off of it. So the electromagnetic flow meters are really cool. Doesn't contact with the fluid. They're fairly cheap to make. Again, kind of a benefit of using a liquid metal. And in the reverse, we can have electromagnetic pumps. So we can now, where we have the electromagnetic flow meters kind of leverage the flowing sodium, we can do the reverse. We can drive a bunch of current across a pipe while having a magnetic field orthogonal to it, and then drive the sodium forward, since we're a liquid metal. So we have electromagnetic pumps. We're able to drive the sodium coolant through our pipes without having any seals, any mechanical contact with it. We're able to measure the flow rate in the reverse principle. So yeah, there's a lot of cool INC with sodium reactors. I would say the challenge with it would be is if the instrumentation is on the primary coolant side, which is actually near the core, and now you have to have a lot of shielding or some materials that are resistant to radiation. And that's where the challenge can be.
Yeah, I imagine you guys do a lot of like tolerance stack ups and things like that. I remember people at Westinghouse doing a lot of that type of work to make sure that even if everything is at like the wrong end of every tolerance, you're still overall the system's within the good limit or something like that.
Yeah, the error propagation can get unwieldy in some applications.
Do you guys test the radiation hardness or like the rigor of some of the CDAC modules and stuff? Because I know when we were at Westinghouse, we had a hot cell and we would zap stuff occasionally just to see how much it would take. Did you guys ever do anything like that?
Sounds like you were having more fun there. No, we don't. We don't have any sources actually in our building right now. So that would be the only aspect of a sodium fast reactor we're not really replicating is the radiation aspect. And just to give you some background to justify it, there's actually two sodium loops. There's a primary sodium that actually transfers heat from the core to actually an intermediate sodium loop. That intermediate sodium loop is non-radioactive or very low in radiation, and that is what transfers heat to your pressurized water to generate steam and electricity. So that's kind of where, just to give background on where we play, what field we play in. So unfortunately, we don't have any operating nuclear reactors on Argonne's campus right now to do that. We do have a hot cell, but I'm not sure what its status is, to be honest with you.
Yeah, yeah. When I worked at Westinghouse, we had a hot cell, and they had some cesium sources, and they would zap stuff. And they were also the other thing they would do is take samples. Apparently, when they built the reactors, they had no idea how metal would react after 40 years of getting zapped with neutrons. So they put in these special sections that they were basically every time they do a service, they cut a chunk out
Oh,
intentionally, and
cool.
then they take it back and they do. I think they called them Sharpie tests. I'm not a mechanical engineer, but apparently that's like a pretty common test to do to
Yeah,
like
yeah,
hit it with a
sure.
hammer and see how it breaks and fractures.
So
So,
how well did the CDAX hold up?
uh, they held up okay. I think for this particular project, if I remember correctly, we had to put them behind some steel plates or lead plates or something. I think lead, and then some steel around it just to make sure that met like the lifetime. So they had like a certain lifetime. They wanted it to last like I don't know 20 years. So we bombarded it with like 20 years in an accelerated form, and then we said, okay, yeah, well, it killed it after 5 years. So if we put X amount of shielding around it, it should work. Somebody
Oh,
did that calculation, not me. I don't know. I just know we built a giant skid and it was very complicated. So one of the issues with INC stuff in the actual like current fleet is putting stuff inside containment and then having it sit there and like you can't get to it because the reactor's running and you can't get in there. Do sodium reactors, I assume, have similar problems?
yeah, they definitely still have everything inside of a containment. There's another person I've collaborated on that is actually looking at, this is kind of related, not so much on Lifeline, but actually using the coolant pipes that leave that
Hmm.
containment and actually using them as almost like a conduit to transmit sensor signals. So you don't have to
Ah,
run
okay.
wires. You can almost do some kind of not wireless, but transmit your signals through the actual pipe.
As
Um,
opposed to putting in penetrations.
exactly, yeah, just for INC and things like that. Um, I honestly can't speak too much on the containment side, though, to be honest with you. Um,
Well, every time we built a new INC system at Westinghouse, it was definitely a big deal if we needed more penetrations. So we were always trying to figure out how we could reuse existing ones. And yeah.
Absolutely, yeah.
And I do remember, this was like earlier, but I do remember like trying to talk about Wi-Fi and stuff because I remember, and I don't, you guys are doing more experimental stuff, so it might not be as regulated yet, but like there was a lot like just running one extra cable required a whole bunch of stuff because you had to like do studies to prove that it didn't interfere with anything else, and then you also had to do like seismic studies for all the cable trays to make sure that you didn't
Hmm.
overload the cable trays, and like it was way more complicated. So it would have been much easier if we could have just wirelessly transmitted signals. But then it was also they were worried about interference that way too. So
Yeah, that's man, I have a friend of mine who works here now. He's worked at a nuclear power plant just in southern Illinois or center of Illinois, and he was telling me a story about how they had a piece of unistrut to support some of the cables, and it was deemed it was safety, and so that it was a safety feature, and so the electrician installing the unistrut actually had to use a torque wrench to torque down the bolt to hold it on. It's
yeah,
just, yeah, the amount of rigor to your point is anytime you have to deviate from design or alter a design, it's just a lot of rigor involved from a safety aspect. Um, I would say, nuclear historically has been analog. It still is for the most part, but is now very much open to a digitalization. And I think that will it's an industry that's going to extremely benefit from increased INC as well as just the digitalization of it. I know I was taking part of a workshop, and uh, this individual, she worked at a nuclear power plant and was talking about how people were oh, it's never going to happen for nuclear. You're never going to see digitalization, and how they never thought they'd see Wi-Fi. And now they do have Wi-Fi in a lot of the support buildings.
ah, that's
Anything
interesting.
safe, yeah, anything safety related is still analog, but something that's more of like operating, I would say the traditional power plant portion of it, the power cycle, supporting equipment, anything that's not strictly safety related, has seen more digitalization. In fact, my alma mater, Purdue University, has the first and I believe only fully digital INC nuclear reactor.
Wow,
Uh,
that's cool.
so yeah, it doesn't generate electricity. It's just a research reactor for the university students. But just to kind of show you, that's where the industry is
Yeah,
realizing they have to head to stay competitive, and they have to find a way
yeah.
to utilize uh, INC more.
Yeah, well, I can imagine, like, in the name of minimizing the number of penetrations, right? If you could somehow put the digitizer inside containment, run all the analog signals to the digitizer, and then digitize it, and then just have one Ethernet cable or something, or
Yeah,
maybe like a pair for redundancy or whatever you would do. That'd be a lot better than passing all those analog signals through all the way back. Which in some
absolutely.
cases I think they probably were doing, if I remember correctly. So the other thing you hit on is interesting with the struts and having to torque the bolts and stuff. There's a difference between as designed and as built, which is very interesting. And we ran into this at Westinghouse. I mentioned the what was it, the AP1000. The part of the design was like the coolant water like evaporates and then collects in these, basically the containment's this big dome. The water evaporates, hits the dome, and it runs down the dome, which is fine, except that when they started building the things, they had to put in all these pipes, and the pipes suddenly needed supports, and the supports were then put on the dome. And when they bolted it on the dome, the water running down, instead of running down the dome, now runs down the pipes and back and doesn't end up where it's supposed to end up. And so that was a big, interesting problem that they had to try to solve. Because I remember us doing all kinds of studies with plates, and we would try to run a film of water over them at different angles and see like what actually caused it to deviate from following the plate and what didn't, and how much got lost. And that was very interesting. But the other interesting project that I worked on, and I left before I saw this project finish, but when they built the new plants they were building in China, and there were a few, I think, in North Carolina and Georgia, they would put all the pipes in, and they have to have a certain slope in order for things to work correctly. And they would install them with the right slope, but when they first turned on the reactor, you get hit with this giant wave of highly pressurized, very hot water, and it would move things. And so they had like a whole series of, like, I don't know, several hundred CDACs or compact RIOs that they would put around the plant to measure different things and slopes to make sure that when everything finally settled, that it settled at the right angle still. So that was
Oh,
an
really?
interesting, yeah. Yeah, it was this big mobile setup that they would do that. So,
Wow.
because they had to validate that once it was built and run once, that like everything did, like it didn't just move and suddenly it was off.
Yeah, I mean, this that is definitely the kind of nuclear energy and or nuclear energy safety environment is like leave no stone unturned. So,
Yeah, I
uh,
mean it's yeah, it's good. New government regulation. Sometimes people are like, oh, it's too much. In nuclear industry, I'm glad that we have it. It can be cumbersome at sometimes to comply with all of it, but for the most part, it was there for good reason.
yeah,
Yeah.
absolutely. And I think we absolutely need regulation. I think there's where we're standing in from a challenge is that the NRC was so used to doing just light water reactors, they don't know how to really license the newer reactors. And so that's the kind of, we've been working and we get along with the NRC very well. We've been working with them of how you need to adapt the current rule set to something now that's inherently safe and has all these advantages, right? Um, that you're not talking about the same, comparing apples to oranges, and you still have rules and regulations that only apply to apples, where we're trying to produce oranges now. So definitely needed, but yeah, we're looking forward to working with them to update for these next gen reactors.
Well,
Um,
it's good to hear you being proactive because I feel like, in general, in the technology space, and I say that broadly, the government tends to be more reactive because the stuff's cutting edge, it's constantly changing, the government's constantly trying to play catch up. So it's good that you guys are ahead of that a little bit.
Yeah, I mean, just to kind of circle back to your point of like, there's a huge difference between designed and as built, right? As
Mhm.
experimentalists and like test and measurement people, we know, the hands-on work involved. And one of the things we demonstrated here was actually using a reality capture. I don't know if you're familiar with that to to actually, we use that on our facility as a way to kind of get as built, which I think is going to be, as the technology it's already really good technology, but as it even gets more refined, it's going to be a game changer for acquiring as built.
So one thing you mentioned was this idea of digital twins. Can you expound upon that a little bit?
Yeah, I think who you're talking to, the definition of digital twin varies. I went to an A&E CAD conference to give a presentation on the work we did, and a lot of people there are trying to claim, oh, a CAD model is a digital twin. It's a representation of a physical asset in a virtual environment. You go, okay, I can see where you're coming from with that, but that's not what I would say we're considering a digital twin. I don't think, there's a digital twin consortium that takes industry and academia and government together and kind of comes together what's defined as a digital twin. And what you find, to summarize that, is there's a lot of elements to a digital twin. It's not just having a CAD model. It's not just having reality capture. It's not just, seeing all of your asset information on some kind of ERP system and self-ordering parts. It's not just predictive maintenance. It's a combination of it all. And so when I look at digital twin, I kind of look at it as they define it as a periodic table of elements of a digital twin from this consortium. And I look at that as more of a journey. It's more of like on a scale of 1 to 10, how close are you to a digital twin? As opposed to, oh yeah, we have a digital twin, So I think of it more of a scale of where, yeah, we're at a 10. Everything is digital, everything's tracked. It's all this big harmonious thing. Where a level 1 would be like, yeah, we have a CAD model. And
Yeah.
so, yeah.
Oh,
So,
okay. Now it's like I'm trying to think of it as like you're simulating this thing, and how accurate and how good is your simulation, and what are the boundary conditions, and where does it leak, and where does it not quite behave like the real system? Am I thinking about that right?
yeah,
Yeah.
yeah. At the end of the day, there's always going to be some error involved. And the less error you have between your digital representation, your physical, I'd say the more refined your digital twin is. I I know where we're shooting to go for, and that is focused because we are able to leverage the physical facility of the mechanisms engineering test loop, is we're really looking to reduce over or construction costs because we went through this construction activity, and we're also looking to reduce O&M costs through digital twin. And what I envision that of being is when I go to adjust the set point on this large facility, before I do that, I have a model of it built that has the physics incorporated. I'm never going to capture all of the physical phenomena in a computer through a simulation, but I can augment that or supplement that with my real world data. So I have a model of my physical facility that's taking my real world data. It also understands the physics, the heat transfer, the hydraulics of the system, et cetera. And before I go to change something on the facility, I can quick run it on that and get real time and get results quickly. Or I can also use that to augment my HMI to my operator. So I have a smaller or a less refined or less granular version of that model. And it's providing virtual sensors to my operator. So I have a physical pressure sensor or a physical flow meter. And then I can't put a flow meter on every single pipe. But if I have my physics is correct and I have data to supply it, I can calculate what a flow rate may be through this pipe and then put a virtual sensor to my operator. So now my operator has much more information to gauge off of. That they have this physical flow meter. Okay, I know this is working. Now I have my quote unquote part of my digital twin, which is now calculating what the flow rate is where there isn't instrumentation, or perhaps supplementing where there is physical as just a redundancy check. So that's kind of where I see one application of digital twins is supporting the now with the operator, predicting the future if they want to change the configuration, or the maneuver that they're going to do. They can see how it's going to be formed before they get to do that. They may, if you can run it fast enough, you may find out, oh, I actually don't want to make those changes. It's going to adversely impact my plan. And then you obviously have all the data you collected to do the pass. So I see all this INC, this data collection, and why I think LabVIEW is kind of resurfacing this area because it's so flexible and the importance of data is you have data that's allowing you is your time machine. You can look into the past, it'll help you in the present, and then you can use it with physics to predict the future. I think it's close we'll get to a time machine in my lifetime. So that's one aspect of the digital twin. I could go on and on about the predictive maintenance aspects of intertwining with business operations of ERP systems, supply chains. I think, as I mentioned, I think a digital twin is more of a sliding scale of how close you are to perfect than it is of, I will guarantee you, Sam, I'm never going to claim we have a full-blown digital twin. I will claim we have parts. Because it is just such, there's so many moving pieces, in my opinion, to a full-blown digital twin.
Another topic that you mentioned earlier was XR and using LabVIEW and GWeb and some web APIs. Do you want to talk a little bit about that?
Yeah, the extended reality actually stemmed from going from a light water reactor to a sodium-cooled reactor. The current nuclear fleet, since they're cooled with water, when they do maintenance, you can actually see through a pool of water and kind of get an idea of where equipment is, what things look like. Sodium is optically opaque. If you drop something in a pool of sodium, you're not going to be able to see it visually. You can use certain techniques we've developed at Argonne to send ultrasonic signals and kind of use a crude sonar method. And so that's where that kind of stemmed from for the applications. Like, well, our operators and our technicians and maintenance won't be able to see a lot of things. It's going to be, one, under a lot of insulation because it's really hot. Two, it's going to be optically opaque coolant. So even if they freeze the sodium and try to look into it, they can't see anything. So how do we provide the operators and other crew with tools to visualize what's going on? And that's where extended reality dawned from. And really, a LabVIEW GWeb enabled me, because I'm not a web developer whatsoever. I did a rough JavaScript code and some CS scripting and all of that to make my own kind of demo web page. And I kind of got, things to work of how I wanted. But going to GWeb was actually, for me, just really great. I was able to replicate, queued state machines and deploy to a web page quite easily. It was using, that LabVIEW develop environment that I was kind of familiar with to generate a web page. It also made it really easy to interact with LabVIEW's web services so I could get the live data through an API we developed. So the GWeb was huge in enabling at least someone who's not a web developer the ability to deploy some extended reality technologies. One example that we deployed was a little barcode tag on one of our assets. And are you familiar with RealWear assisted reality booms? So RealWear has a product that they call assisted reality. And basically all it is a very small tablet screen that runs off of Android that goes just below your eyes and your peripherals.
Ah.
It's got kind of a headband on it. You can mount it to a hard hat. I used to have it in my office. I should have brought it. But so you basically have a little screen. You can look in your peripherals, but it's when you look in your peripherals, it's a fairly larger screen. You can kind of see it. And it's also got a built-in camera. So you're able to scan the QR code of our asset. It recognized the link. It took you to a GWeb link, and in their peripherals and their screen, they could actually see what the asset's make and model number was, what its serial number was. They could interact with our computerized maintenance management system, so they could see when that asset was last had a PM performed on it, what parts were replaced, and then they could also go to a different tab on the, again, all done in GWeb. They could go to a different tab which showed the LabVIEW data. Again, so someone could be manipulating a valve or holding some insulation up, turning a valve, and in the peripherals they could actually see what the pressure was or what the flow rate was real time in a graph or a numeric indicator. And that was all done through GWeb. Because that's all that QR code did. It took you to a GWeb page. I'm trying to think. We've also done with GWeb and the extended reality and that hardware. We also did a digital procedure. So historically, the nuclear energy industry is paper trail, paper-based procedures. How do you digitize that, and what are the advantages going to be? And so we took one of our procedures and digitized it. Again, through their peripherals, they could go through a procedure, mark check boxes audibly, see real-time valve positions, real-time data. And a benefit of that is you no longer have someone just kind of signing off or checking it. If there was a sensor that wasn't reading correctly, you could prevent them from moving to the next step, right? If it's like, oh, all of your temperatures need to be at this value, all of your pressures need to be here. Okay, yeah, it looks good. I'm going to try to go to the next page. Why is it not letting me know? You can see right there real time, you're not meeting the criteria.
Also for recording values probably too, right? So you're not like writing down stuff. Yeah.
Exactly. Yeah. So you're not recording. It's automatically going to a database. We interact with our computerized maintenance management system so they could complete a work order from it and, check the boxes, check out what parts they used. All while it's still having the ability to use their hands, which I thought was critical for a technician. As someone who does hands-on work, I'm not naive to the fact that holding a tablet or carrying around a tablet is kind of a nuisance. But if I have something attached to my hard hat, I can talk to it. I can get data from it. I can actually have a camera live feed to an expert. Was beneficial. We also used the Microsoft HoloLens, which they kind of dropped out of the game. They're focused mostly on military applications, to my knowledge now. It's just strictly a DoD thing. But we had a couple HoloLens applications. And then we also used tablets and cell phones using software from PTC called Vuforia, which was able to augment our CAD models real time. And that was a cool application. That wasn't really interacting with LabVIEW at all. That was just basically, if you have a construction drawing, it's going to be obviously 2D, and you're going to try to communicate to people how this complex piping network of your reactor plant is supposed to all fit together, because it's all going to come in these sub-assemblies, and now you got to go, okay, yeah, part B goes to, connector B. And with augmented reality, you're able to just hold up a tablet or a cell phone, and it would augment how the piping is supposed to be laid out to scale. So now someone could just, okay, this assembly is supposed to be oriented in this fashion, and it goes here. So we demonstrated that, as well as some kind of fuel handling techniques as well, to show the fuel assembly actually being pulled in and out, or the gears actually rotating on the machine. And we used the LabVIEW data to display like vibration and speed of the machine. So those are kind of quick examples we did with extended reality. But I think that's space where I think LabVIEW is also going to potentially play the fact of it's so easy to get data out of LabVIEW, as opposed to some other kind of INC equipment or SCADA equipment that's more locked down.
Yeah, what immediately popped in my head when you were talking about that was like, you mentioned like looking down and like the sodium's opaque. I imagined like trying to tighten a bolt or something, right? And the VR could know right where the bolt's supposed to be. And as you put the wrench in, it could like project the wrench and be like, okay, yeah, it looks like you're on it. And then, you start turning, you feel the resistance. That's kind of the immediate application that I was thinking of.
No, you're spot on, Sam, because that's exactly not like, that's a good idea of like showing it where it is, where you can't see. They've also done it to like make sure you're doing the correct torque pattern. I think in the future, you'll also see smart tools. So since, as we become more digitalized and we're starting to have these wearables on us, that it's going to connect with tools that actually have a recording. So not only is it going to help you locate the bolt, but as you tighten and torque it, it's going to digitally record that torque value to a database. And so when you're talking about this high level of QA, you're going to streamline your QA, because you're no longer, okay, yeah, I torqued it to 80 foot-pounds. I put it in this paper, or I, manually entered it in. It's just there's not going to be any forging allowed. There's not going to be any, human error because it's going to come direct from, securely from the machine to a database what the torque values were. So I think there's a lot of cool things that are going to come from digitalization and help the industry get streamlined.
Yeah, I mean, back to our whole thing about regulations and stuff, right? If that helps that whole process go faster, and then the regulations are less onerous. Because I remember, like in the old days, like nuclear stuff, like one person would have to read it, another person would have to like repeat it, and like you repeat it 3 or 4 times to make sure everybody was on the same page before you wrote anything down, and like, yeah, there's a lot of that I think could go away.
Yeah.
Yeah.
And I think it's, what we talked about earlier, how it's important to have regulation. And then if you can have regulation and it's not, impacting your efficiency, that's the best of both worlds, kind of taking it
Yeah,
easy.
absolutely. I do have another question though. You mentioned people like doing maintenance and stuff, and maybe dropping something in PWRs. Loose parts was actually like a really big deal. We had like whole systems of microphones and stuff that I worked on like around the plant to try to detect like what parts were loose and where they were and were they going to cause problems. Is that still an issue then? I guess it must be.
So because sodium fast reactors can't really be exposed to the environment, oxygen is actually our primary contaminant of concern. So we always want to keep our sodium under a cover gas and sealed. I don't think it's going to be quite as big of an issue. However, it is still an issue to the fact that, like I mentioned, the company or Argonne company, Argonne has developed a technique to view under sodium by using, these ultrasonic signals and measuring the time of flight intensity because loose parts are an issue still. I don't know that they'll be as big of an issue in PWRs, but I actually think was it like a mistress system you were using for the loose
Uh,
parts?
it was called DMIMS DX, but it was basically just a bunch of accelerometers.
Okay.
So yeah.
Yeah. Yeah, I think it's like 'cause you're trying to listen for things bouncing around,
Yep,
right?
exactly. Yeah. Yep. No, but to your point though, yeah, like even with the sealed system, I think you'd still have issues because the one of the things that we found is that there was an issue with like there's some baffles somewhere and like they were held in by bolts and they vibrated so much it sheared most of the bolts off and then the bolt heads were floating around. So like that was not like somebody dropped something in or whatever. Which that
Well, yeah.
always just like it blew my mind that that was a thing, but like like you just don't think about it. But yeah, I mean, people have like drop a bolt, a wrench, have loose change in your pocket or something. Like it's a big
Or
deal. Yeah.
yeah, as you mentioned too, I was surprised too. Like when I was first shown the technology, I was expecting it to be kind of this thing in the background, right? And it's like a station someone's sitting at with the headphones a lot of times too, of like if they really have to listen for something to kind of
Yeah.
have a human intervention.
Yeah, this one would detect it automatically, but they did have a set of headphones that you could put on and listen. That was one of the you mentioned like AI stuff, I think at some point, and like that was something where I thought would be a good application for AI because they were basically just like they would look at the frequency spectrum and they would bin it and they would just compare it to like known things. But like I always thought they could do much better than that with some sort of AI fuzzy matching type stuff. But
No, I 100% agree. There's something very similar as we worked with the University of Illinois at Chicago, actually what's called like a structural health monitoring, and it also listens for microfractures within the metal or a piping system or a vessel. They do the same thing. They have a certain signature, and they can tell, yeah, that's actually enough atoms displacing or being dislocated from the lattice that your equipment's going to fail soon. So I think that's another huge AI application, as you mentioned, kind of discerning whether it's just background noise or an actual event based off the spectrum.
a couple last questions to wrap things up. In some of the questions I'd asked you earlier, you mentioned something about refactoring in LabVIEW. So do you spend a lot of time inheriting other people's code or doing research? I would imagine you're writing a lot of new code or some of both.
It's it's a little bit of both. I mean, some people come and go and they had a little project, and so you kind of need to pick up where they left off. I think personally, what I found interesting about refactoring is just my own work, is that that nothing is perfect the first time around, whether it's software development, hardware development. At the end of the day, we're all constrained by budgets and time, and you have to get something to work at the end of the day. You want to exceed your minimum viable product, but a lot of times that's just not feasible. And so what I liked about refactoring is kind of establishing a framework and it really not just a framework, but is you can start to communicate that this is the process to upper management so that you allocate future funds and time to perform refactoring. I think is important because it's really formalizing the process as opposed to just like, hey boss, or hey senior management, we need more money to do this. Well, I thought it was working. It's working, right? Like, yes, it's working, but not as good as we'd like it to, or here are the certain things that we really think we need to restructure to ensure its longevity. I think formalizing it through refactoring is something I'd like to start doing for, again, as I mentioned, talking with you earlier, it's not only just software development, but hardware as well. Because at least maybe it's just my incompetence, but I've never had anything, come off the line absolutely perfect. So.
Yeah, well, that makes a lot of sense. So I feel like refactoring actually kind of has two applications. One is I inherited this old code and it's old and it's crusty and it's just like the way they did it is not the way I would do it, so I'm going to change it. But there's also I'm doing an R&D thing and I can't know everything ahead of time, so I have to take my best guess and write the code. And then when I realize that that's not the right code or that things have changed or there's some new variable I didn't think about, then I can go back and refactor my own code and change it, even though like I'm not refactoring because it's junk code or anything like that. I'm refactoring because the situation has changed.
Absolutely. And we run into that as well. There's some machines here that are still running like Windows XP because that machine only interacts with XP. It didn't, and they don't really make them anymore. And so there's actually some pretty high profile experimental machinery that is in need of refactoring. Because, and again, code update, hardware update, you name it. And again, just to regurgitate what you said, it's not that we're not saying it's bad. It's just you have to. Always in the mindset of continuous improvement. Mm-hmm. Just because something is working doesn't mean it shouldn't be, continuously improved.
Well, also, I would say the fact that you're actually contemplating refactoring it tells you that it's actually doing something useful, because otherwise you'd just like throw it away and be done with it and walk away and be like, yeah, okay, yeah, this crappy code over here, we don't need anymore, just throw it away. So it's doing something useful.
Very valid, yeah. Yeah, it's generating value at the end of the day, and if you want it to keep it generating value, you need to incorporate refactoring. Yeah, I like that approach.
Okay, so this next question, you feel free not to answer, but I gotta ask, like, do you want to make any predictions or of like the future of nuclear energy? Like, when are we actually going to see a liquid sodium reactor or any of these small modular reactors going to happen anytime in the near future? And or like, what are the major roadblocks that are still left to get us to that point?
I will start with the roadblocks so that at least someone's not just saying I'm a pessimist or an optimist, that there's some context. I think the supply chain needs to be, reinforced and kind of reestablished. The fact that, it was always this thing that was blamed when it went wrong. They're just like, it's terrible. They don't know what they're doing, even though, we've had an extremely safe record. But it was never praised for supplying the United States with so much clean energy safely, and reliably for all these years. And when something went wrong, like Fukushima, it was always this oh, it's bad, and you don't give the praise when it deserved praise. So given that a lot of people kind of went away from nuclear energy for so long, that supply chain weakened. So I think first things first, you need to get the supply chain back. And that's not only the actual components of reactor grade components and radiation resistant materials, but also the personnel. Nuclear is a very trade intensive endeavor. We need pipe fitters, welders, electricians, There's a lot that goes into a nuclear power plant. It's just not, a bunch of people sitting around a reactor plant, moving control rods up and down. There's a lot of people that go behind the scenes to making these large scale plants going. If we talk about small modular reactors or microreactors, more ones that are going to be more fabricated off an assembly line or more factory built, you're going to have specialized factory workers. It's not just going to be, someone just monitoring the machine in a control limit chart and stopping the machine when it gets out of control. You're going to have personnel that are familiar with nuclear components and nuclear technologies. You also have to have sodium experts, and that's what we're trying to develop here, is the fact that sodium, I don't find it that unsafe. It's we handle it here all the time. We actually set it on fire to dispose of it. So we regularly have sodium fires. That's like the big thing. Anti-sodium people say, so, oh, sodium sets on fire. And, what are you going to do when it's on fire? We set on fire all the time. We mitigate the fires. We can snuff them out. It's all about education and experience. And that's something we're trying to provide here as well with sodium. So that's my long-winded kind of first start, is the supply chain from a component and personnel aspect, is that we don't just need nuclear engineers. We need a lot of support people. A lot of times it's well-paying jobs that don't require college degrees. And again, a very rewarding career to help supply the world with clean energy. I think education of the public. A lot of people hear radiation. You, with your background in Westinghouse, probably is not as scared as most with radiation. Understand that it is dangerous, but it shouldn't be feared. It should be respected. I have two little girls. I kind of regurgitate to them about water. Don't be afraid to swim. But you can't be afraid of water, but you gotta respect it. That water can be, dangerous if you're not, if you're going in adverse conditions. So, I do think we'll see sodium fast reactors, as I mentioned. TerraPower is making great progress on their power plant. We're supporting them in various ways here at Argonne National Laboratory. You have Oklo, which is another company making a kind of smaller than TerraPower's, but they're also making great progress, aimed to have an installation at Idaho National Laboratory later on. So I do think you'll see them. I think it will take time until it's at like a proliferation, but you have to cut a path somewhere. So I don't really want to put a date personally on when I think you'll see the first or a bunch of them. I can tell you there are challenges we're working on. As I mentioned, an update to the NRC to handle sodium fast reactors, I think is much needed. And again, not that they're doing anything wrong. They've kept us safe for all these years. And I think they're very much aligned too, that they're working with us to try to learn more about sodium. So it's not this like bashing. It's more of a mutually like, hey, we need to adapt. We need to also update our systems as well. So yeah, I think you'll see it. But those are some challenges. We already talked about the autonomous operation, increasing the I&C, and having the regulatory framework to support that. I think that will be huge. I think personally, again, not a reflection of the laboratory or the Department of Energy, but personally, I think once you improve the supply chain and you get more autonomous, more I&C, I think you're going to see them all over the place. Because like I said, we actually talk, I'm involved in a cybersecurity project right now. And why I'm mentioning that is when you talk about the previous reactors and cybersecurity attacks, you're focused on something malicious where you're going to cause damage to human health, the environment. With the new generation of reactors, since things are inherently safe and the physics are working to advantage, we're not concerned with cyber attacks from adversely impacting the environment or personnel. We're more concerned about a cyber attack shutting down the plant and harming its economic viability. just to give you context of like, that's the concern. It's not really the safety, the environment, it's the economic feasibility. And I think once you have a robust cybersecurity, supply chain, autonomous operations, I mean, your fuel can last for decades. So it's and it's clean energy, and you're able to recycle a lot of the spent fuel. I mean, literally, I feel like all the challenges can be solved. It's just a matter of deploying the technologies.
Yeah, that's definitely a thing because spent fuel for existing nuclear power plants is definitely an issue. I remember there was something about, was it Yucca Mountain or somewhere in Nevada where they were going to store all the stuff and then they decided not to, and like the spent fuel pools were filling up, and I don't know where that eventually ended up, but I do know that's on their radar as something that needs addressed. So
Yeah. And as of now, it's still not that much. I think the last kind of statistic I heard is it fills up a football field, from a area wise, and maybe it's like 20 feet high or something like that. So even when we look at, that's another thing we like to talk about in nuclear energy industry is people are so focused on, what they consider waste, which is spent fuel, that well, it's kind of either that or all the emissions that you're breathing from hydrocarbon fueled power
hmm
plants, right? Like just because you can't see their waste doesn't mean it's not there. It's there, you know. So I think nuclear is definitely an attractive option from that standpoint.
So, if people want to learn more about all this stuff that we've been talking about, you are going to be presenting at GDevCon N.A, correct?
Yeah, I'll be presenting on the first day. I believe it's a Tuesday, and I think the second one to go is around like 10 o'clock or something like that, 10:30. And so I'll just be presenting on how LabVIEW is used in a large application like Metal that has well over 100 IP addresses, various users of it, and the IT infrastructure required to integrate with all this OT equipment, as well as some of the security aspects of working with more of a web-based interface of users using extended reality technologies, transferring data to different sites within campus that are doing machine learning and AI kind of monitoring of the facility. So that's kind of what the focus will be on. And then, just general information on the facility. We do have a website. If you kind of just Google Argonne and METL, it'll probably pop up, and we have a lot of videos on there. Crowd Pleasers is one of us burning sodium. So that's always been kind of a hit. But we also have videos that go through a virtual tour of the facility, as well as a lot of reports that go into more granular detail.
If you want to check out Derek's presentation, along with the many other presentations that will be available at GDevCon N.A, we still have tickets available for the conference. You can get tickets by going to www.gdevconNA.org, and the link is in the show notes. Hopefully, we'll see you in Chicago this summer.
All right. Well, thank you very much. It's been a great conversation.
Yeah, thank you so much, Sam.
That's it for today's episode of the LabVIEW Experiment. Thanks for listening. If you have any comments or questions, head over to thelabviewexperiment.com and drop me a note. And don't forget to subscribe to the podcast and follow us on Twitter and Instagram at the LV Experiment.